For some reason the recording stopped. All right, so back on. So yeah, I talked about the assessment and everything and all the assignments coming up, and the workbook is due Friday. The workbook assignment is due Friday. So those are all the things coming up as well. So other than that, let's go ahead and get started. So also, additionally, I went ahead and updated the course notes. You will notice at the end of what you may have already downloaded or printed out, I did add more notes, all the notes leading up to the midterm. So you will notice those at the bottom of the notes here. You're welcome to print them out, whatever the case may be, but I will, as you know, I'll be going straight from these, as I will pick up on as of right now. So we're going to be talking about linear equations and inequalities. And a lot of this may seem familiar from previous stuff that we have done. So this kind of looks at it in a more formal environment, and mainly throughout this section, I will be talking about the least common denominator. That seems to be the most prevalent algebraic situation. So sometimes we need to simplify various problems, such as the simplification techniques may be involving combining like terms, distribution, FOILing, and using an LCD, or a least common denominator. And mainly I'm going to focus on the last one, but elements of the previous three will come up quite a bit as well. But mainly I think the least common denominator is what needs to be focused on the most. I did also leave a note about how to handle expressions such as x plus 3 squared. I know there's a few homework questions that will bring that up. And it is not true that the exponent just goes directly to the terms within the parentheses. You have to actually write it out twice and FOIL, like this, in order to get your final answer. But besides for that, let's move on to the least common denominator itself. And this is something that we will be using throughout the whole class, this whole semester. The least common denominator, it's the least common multiple of all the denominators involved. And I wrote an important note down here of what the LCD, what the least common denominator is trying to do here, why we use it. So I wrote here, we find the LCD for any equation involving a fraction. If I see a fraction, you're going to hear me say LCD. That's going to be a fairly consistent thing. Once the LCD is found, you multiply it to every term in the equation. And then pretty much the kicker here is after you use the LCD, after you apply it correctly, you should not have any more fractions in the problem. It's our way of simplifying it to where all the fractions will be gone after we apply it. So it's a very important initial step to clean up the problem before we continue with it. And you might notice examples 1 and 2, those have fractions. So naturally, we want to find the least common denominator. So the least common denominator, it's the least common multiple of all the denominators involved. The denominators here are 3 and 4, obviously because they're the denominators for their respective fractions. So we need to find the least common multiple of those two. What is the smallest number that 3 would go into or divide into? What's the and simultaneously 4? Yeah, so it's going to be 12. So when I say go into, I'm going to use that terminology fairly often. So it ends up being 12. And the reason why is because that 12 divided by each denominator gives us a whole number. That's how you know that something goes into another number. So 12 divided by 3 is 4. It's a nice whole number. That means that 3 goes into 12. 12 divided by 4 is 3, which is a nice whole number, which means 4 goes up to 12. And this is kind of the game that we play, at least for when all of our denominators are numbers. So we can take exactly that. So I'm going to just rewrite the expression. But I'm going to multiply each one of these by 12. So exactly in that note I said was, once we find the LCD, we multiply it to every single term. And when I say term, I mean things split up by pluses and minuses. So that x plus 4 over 3 is one term because it's one fraction. It has terms in it, but it itself is one term. You even multiply it to terms that don't have fractions. That's the way of balancing the equation. And so the next step is, well, we do this so we can get rid or cancel the fractions. So that means that this 3, we're going to have to get rid of that somehow. And that fraction and the LCD are immediately associated with each other because we chose the LCD to where this fraction of 12 divided by 3 will give us a nice whole number, which is 4. That's why we chose the LCD to be so specific. It's because we want this ratio of the values to be a nice whole number. And then from there, we can simplify it very nicely. So I see a 4, I see an x plus 4. That's what's left over, at least for that first fraction. So I see a 4, and x plus 4. I'm keeping the numerator in parentheses because that is one concrete thing. The numerator is one concrete expression. And that takes care of the first fraction. Second fraction, it's the same idea. We need to cancel out that 4. The LCD associates with it very well. 12 divided by 4 is 3. So that means now we have plus, so the plus sign follows. And now we have 3 times parentheses x plus 1. And then that's equal to 3 times 12. There's nothing we have to cancel, which fine, whatever. We just perform the arithmetic here. 3 times 12 is 36. And notice, now that we've applied the least common denominator, now that we've applied it, there's no more fractions. That's exactly what we wanted. There's no more fractions here, which means all we have to do is focus on, say, distribution and combining like terms. So here we seem to get 7x. Let's see, we get 7x. Yeah, plus 19. I feel like I got a different answer in my last section. Uh-oh. Let me just work it out for now. Oh, wait, no, this is right. This is right. Okay, never mind. Okay, this is good. Yeah, so here, we can solve for this fairly quickly. 36 minus 19, that should be 17. And then x is 17 divided by 7. Kind of using the prerequisite, combining like terms and solving for x stuff. Okay, so that's definitely right. Okay, So if that's okay with everybody, or if you're still confused on that, let's go through example 2, and then I'll ask any questions you may have. So example 2, I see fractions, no matter what the context is, and I generally think LCD. Now the denominators that are involved are 3 and 9. So naturally, I need to find the least multiple of 3 and 9. What is the smallest number that both 3 and 9 go into? It'd be 9 in this case. It'd be 9 in this case because, well, if it were 3, well, 3 goes into 3 just fine, but 3 divided by 9 is not a nice whole number. In fact, it's a fraction, and the whole point is to make sure the fractions are gone. So it's going to be 9 here, because 9 divided by the first denominator, 3, 9 divided by 3 is 3, that one's good, and 9 divided by 9 is 1. So we get all whole numbers. And we'll see that a little bit further. So I'm just going to rewrite it. And now I'm going to multiply everything by 9. So once we find the least common denominator, we multiply it to every term, whether it has a fraction or not. So that's why I'm multiplying every term by 9. And so naturally, the next thing is we are going to cancel out the fractions by seeing how the denominator interacts with the least common denominator. So here we have the 3 and the 9, and one's in the numerator, one's in the denominator. So naturally, this is a ratio. So 9 divided by 3, it's just 3. So it's just 3. So the way that we can slowly start to build this new function or this new equation is see what's left over. See a 1 times an x times a 3. So that's 3x. The next one is pretty straightforward. It's -5 times 9, which is -45, minus 45. And then equal sign follows. See 2 9s, and they just immediately cancel. So cancel, it's pretty much just 1. So yeah, so what's left over, there's a 1, there's a 4, and there's an x. So naturally that would be 4x. So after you apply the least common denominator, the problem works out very nicely. And from here, we can go ahead and combine like terms. Minus 3x, minus 3x. That's -45 is equal to 4x minus 3x is just x. And we're done. Oops. Does anyone have any questions about either of these two, where all the denominators are numbers? It's pretty much this process. You find the least common denominator, apply just like this, and it should work out very nicely if you applied everything correctly. Let's go ahead and move on. So we're going to take it up a step further by now incorporating a variable as one of the denominator terms. So before we had all numbers. Now we have a variable involved. So let's see how that may affect things. So I see fraction, I instantly think least common denominator. I see 3 denominators. I see a 2, an x, and a 6. So we have two different types of objects here. We have, of course, numbers, and then we have a variable. So for the numbers, let's figure out the least common multiple of the numbers. Let's pretend like the x isn't even there for a second. So with the numbers, yeah, it'd just be 6 to start off. Because what is the smallest number that 2 and 6 both go into? It's just 6. 6 divided by 2 is 3, which means 2 goes into 6. 6 divided by 6 is 1. 6 goes into 6. So that takes care of the numbers aspect. But now we're left with this x. And so with the variables, we need to put an x to compensate for that additional x. We need something to cancel that x in order to get rid of all the fractions. That's why I'm putting an x here to take care of that x. We'll see how this is important in a bit. But that's the slight modification so far. So I'll go ahead and rewrite this. And now I'm going to apply this least common denominator. You multiply every term by the least common denominator. And so now we want to see how that least common denominator associates with the current denominator. So we have 6x and a 2. So naturally, we are combining the numbers together. So that's ultimately 6 divided by 2, which is just 3. And in particular, 6x divided by 2 is 3x, because the 6 divided by 2 is 3. So what are we left with? Technically left with a 1 and a 3x. So that's just 3x. For the next one, that x cancels out with that x. That's why we threw in an additional x into the least common denominator, was so that the x's would cancel. Then we're left with 6 times 6, 36. And so finally, I see an equal sign, and this 6 and this 6 cancel, leaving us with just 5 and an x. Yeah, 5x. So again, LCD gives us a lot of not so nice looking scratch work, but upon applying it correctly, the problem simplifies tremendously. And so finally, we can go ahead and combine like terms. So x is 18. So that's the first example of incorporating numbers and variables into our LCD. Does anyone have any questions so far? Okay, we'll move on to example 4, which seems to be all variable expressions as denominators. So, if anything, we ask ourselves, so as you can notice, we're slowly taking this a step further. Now we have an expression, so expression with 2 or more terms as a denominator. The question is, what's the least common denominator? Well, all of our denominators, we only have one denominator. That's not 2 denominators. That's one concrete denominator with 2 terms in it. So the one denominator is x minus 1. So naturally, the least common denominator have to be the only thing there, the x minus 1. There's no numbers that we have to compare. We don't have to think about, well, how do we compensate for this term and that term? There's only one thing. So that has to be the LCD. So it's just x minus 1. We'll see how to apply that shortly. So we're going to multiply every term by x minus 1. And now that there's more than one term, I'm also going to be safe and put it in parentheses, because this is one LCD. We haven't had to worry about this before because every LCD we've had has been one term. Now we have one LCD that has two terms in it. So that's why I'm using parentheses to stay safe. You can do this consistently if you want. It doesn't change anything. We'll see why that matters more in a bit. So we multiplied every term by the LCD, and we need to see how this cancels with the various denominators. So there's this x minus 1 over here, which of course cancels with the x minus 1 LCD. And all we're left with is just x. That's pretty easy. And then we have 9 times x minus 1, because there's no cancellation. So I'm just rewriting it. There's nothing really to cancel. I can distribute it in a bit, but I figure I'll just write this intermediate step for now. And this is a good reason why it is recommended to use parentheses when your LCD starts to expand in terms by more than 1. You have to end up distributing that 9 to the x and the 1. So if you don't put parentheses, you would not be able to see that. And so finally, for the last fraction, the x minus 1's cancel, and you're left with just a 1. And so this cleans up a lot better than before. So we can go ahead and apply the standard algebraic steps here. How do I get 10? Try it again. There we go. So we simplify it using standard algebraic stuff, distribution, like terms, all that fun stuff. And we get that x is equal to 1, which is wrong. And you might think, well, that just kind of came out of nowhere, so why is that wrong? And so the reason why this is wrong is because of the unfortunate situation we have to deal with whenever we're dealing with fractions. When we deal with fractions, especially, well, in particular, when variables start showing up in the denominator, is sometimes we might end up having a situation where we divide by 0. In the previous problem, we didn't have to worry about this because we had x is equal to 18, and 18 going into the x position would not result in 0 in the denominator. So naturally, this x is equal to 1. If we were to plug that into, say, this fraction over here, we would have 1 divided by 1 minus 1, which is 1 divided by 0. Uh-oh, that's not good. We can't divide by 0. So this happens sometimes where we work out a problem, we get an answer, you're sure you did all the steps right, and my math lab is telling you, no, there's no solutions, I promise. And so that's when we have to reject this answer, say, no solutions. That's the true answer. So you could do all of that work, and you end up just rejecting the one answer you got at the end, which means you would have no solutions. That does happen, and I just wanted you all to be aware of that situation. So if you were wondering why your answer isn't working, this might be the case. We'll see another example of this show up in a bit, but does anyone have any questions so far? If not, let's scroll down a bit and do problem 5 here. So problem 5 is pretty interesting because we have denominators. So we're slowly taking these up a step further. The issue with number 5, before we even do the LCD, is the fact that the denominators are not written in an appropriate form. And when I say that, I mean that x squared minus 4 here can be factored. That is a quadratic. We can factor it. And in fact, it would be in our best interest to factor it for reasons I will explain momentarily. Now, you definitely need to recognize that this is a difference of 2 squares. This is a prerequisite idea from before. And so a difference of 2 squares it tells you that the factorization is precisely x plus the square root of 4 and x minus the square root of 4. The reason I'm picking 4 is because there's a 4 in the problem. Square root of 4 is 2, so that's why I have 2's here. So we can do that for both of these fractions here and here. And so I'm just going to go ahead and start writing out this with the new information that we have. So I went ahead and just exchanged all those denominators with their factored counterparts. There's a reason why trying to check for factored parts is important. It's because it helps us find the least common denominator a lot more easily. In fact, it makes finding the least common denominator possible. So now we have really 2 unique denominators. X plus 2 times x minus 2 is one denominator. We just happen to see it twice. And x plus 2 is the other denominator. Now, our least common denominator needs to have a component for each factor. So I see x plus 2. So naturally, I'm going to add in x plus 2. And now I also see, so that was x plus 2's. So for all of those factors I see, all I have to do is put one x plus 2. I also see x minus 2. And for all of those, I just put an x minus 2. I'm going to be using the space here for the problem. We're going to do problem 6 next. I'm just going to do it on a separate sheet of paper. So all this space that I'm writing is going to be reserved for problem 5. We'll do problem 6 actually over here. We'll get to that though. So we have the least common denominator. So naturally, we can go ahead and multiply every term by said LCD. So we find the LCD, we multiply every term by it. And so naturally, there's going to be a lot of cancellation. X plus 2, x plus 2, x minus 2, x minus 2. That first term, we just get 5x. Next one, yeah, we just get 10. So x plus 2, x plus 2, x minus 2, x minus 2, we're just left with 10. For the last one, only the x plus 2's cancel, which means we're stuck with 4 times x minus 2. So minus 4 times x minus 2. So from here, it's just a matter of distribution, combining like terms. So distribution. So now we have 5x is equal to 10 minus 4x plus 8. Then we have 9x is equal to 18, and thus x is equal to 2. So I added 4x on both sides. 5x plus 4x is 9x. And then 10 plus 8 was already on one side. So 10 plus 8 is 18. Divide both sides by 9, we're done. X is equal to 2. Now we ask ourselves, do we keep this answer or do we reject it? So the question is, if we plug 2 into one of these denominators, will we end up getting 0? Well, if anything, this denominator looks okay, because of course 2 plus 2 is 4, that's not 0. What about this denominator on the far left here? 2 squared is 4, 4 minus 4 is 0. Oh, yikes. So we reject this one, just like we did before. There's no solutions. Oops. So there's no solutions. So that's okay if that happens. It's just we happen to find an extra or an extraneous solution, which we inevitably have to reject. So for those of you who start doing the homework and then start spamming the no solution button, I mean, I can't dissuade you from doing that, but hopefully at some point you realize why no solution is the answer. Yes?
Why is it no solution?
It's no solution because the one solution we found that was 2, we have an issue with fractions. We have an issue of dividing by 0. So that's always bad. So for the value that we found, so let's back up a little bit. So you were okay with up to x is equal to 2, right? So the issue is with fractions, now we have to worry about checking our answers, because we might end up with fractions accidentally dividing by 0. So you have denominators like these two. So x is 2. So what happens, say, if you were to plug in that x is equal to 2 into, say, that denominator right there? So x squared minus 4 becomes 2 squared minus 4. Well, what's 2 squared minus 4? See, 2 squared is 4. 4 minus 4 is 0. That's happening in the denominator. It's not good. You can't have a 0 in the denominator.
You have to go to the beginning of the problem and look at the...
That's right. You have to check your answer at the beginning of the problem and see if it gives you a divide by 0 issue. So you don't have to plug every 2 into every x all over to check it. You have to really just look and see, and you can check the denominators themselves and think to yourself, all right, does the value that I got, does it put a 0 in the denominator, any denominator here at the very beginning? If the answer is yes, then you toss it. If the answer is no, then you keep it. Here, the answer is yes, so we have to toss it and say no solution. So this is something that will be fairly characteristic with this section. Just having to go back and check and make sure that the value you found does not give you a 0 in the denominator. Any other questions from anybody else? Okay, so, yeah, so a few people asked as well. So if you're wondering why there's no solution, you're not the only one, but hopefully that additional explanation helps. So let's look at, so I erased problem 6. We're still going to do it. I just needed the space. Off to the side here, this is what the problem is. And this will be another situation to check the answer at the end and see if it works or not. So here's the problem. I'm, of course, going to do it off to the side so I can have a bunch of space. The first thing I'm going to do is factor any denominators if I can, like I did in the previous problem. X squared minus 1 is a difference of 2 squares, as we mentioned before, except instead of x squared minus 4, it's x squared minus 1, which means we're looking at plus or minus the square root of 1, which is x plus 1, x minus 1. Over here, for the middle denominator, all we have to do is factor out the common x. And over here, we factor out the common x. Those two are also referred to as reverse distribution. So I'll go ahead and rewrite it with all the corrected denominators. And simultaneously, let's go ahead and figure out what the least common denominator is. Well, we have 3 denominators. X plus 1, x minus 1, x times x minus 1, and x times x plus 1. So for each component that I see, or each factor that I see, I need to populate the LCD with it. So, for example, I see x plus 1 and x plus 1. So naturally, I'm going to put x plus 1. I also see x minus 1 and x minus 1. And I see one more. I see an x. So I'm going to throw in an x. So that's why factoring those denominators is helpful, because it allows us to see the components. That way we can build the least common denominator from each one of the factors. So if anything, now we know what to multiply to each fraction. And so naturally, well, hopefully there's a lot of cancellation, as there will be. X plus 1, x plus 1, x minus 1, x minus 1. We're left with an x and another x, which is just x squared. I see an x and that x minus 1 and that x minus 1. So naturally, we are going to be left with x plus 2 in parentheses, numerator's got to stay contained, times x plus 1. Sorry. So let's see, right here for now. Okay. And so finally, we move on to, let's see, there's an equal sign. And so x plus 1. And there's a -2 times x minus 1. And now here's the simplified form. So from here, we just apply the typical algebraic steps. Here we have to FOIL. This is a FOIL situation. And over here on the far right, we have to distribute. So remember with FOIL, it stands for first, outer, inner, last. X times x gives you the x squared. The x times 1 gives you x. 2 times x gives you 2x, and then 2 times 1 gives you 2. I left all of that in parentheses because the negative sign still needs to distribute to all of it. There was minus the FOIL, so that means we have to distribute that minus sign to every single term, which is what I'll do next. So distribute, 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 distribute. Which ultimately changes all the signs. X squareds cancel. Negative x minus 2x is minus 3x. Minus 2 is equal to negative 2x plus 2. We can go ahead and add 3x on both sides. So that would be negative 2 equals x plus 2. So then we get that x is equal to negative 4 when we subtract 2 on both sides. I think that's probably the most hardcore problem in the homework. So don't think every problem's like that. So the final question is, do we keep it or do we reject it? By it, of course, I'm referring to negative 4. So if I plug in negative 4 into every denominator, will I get a 0 at all? The answer is no. We can keep this answer. So remember, it was negative 4. We plug in negative 4 into here, into this denominator. Negative 4 squared is positive 16, minus 1 is 15. Doesn't sound like 0. Over here, you would get negative 4 squared is positive 16, minus negative 4, so you would get 20. And then over here, you would get 12. So none of those are 0. We plug it into every denominator. None of those give us 0. So we can keep it. So we keep it. It's negative 4. Does anyone have any questions about this before we move on? So I believe 2 word problems. So we're gonna switch back. Oh yeah, the symbolic stuff. Okay, so there's also a few questions that, yeah, I know I've gotten an email or 2 about some of these, and so I also moved the homework back. I didn't mean for the next homework to be due on the 9th. The linear equations and inequalities I had to do for the 9th, just before the hurricane happened. I pushed that back a few days. So just keep that in mind. So that should be active now. But yeah, there's some of these symbolic problems in this homework. I think there's 4 in total, and I'm going to do these 2. So as you can see, they're symbolic because there's a bunch of symbols. And so at least for the first problem, what I like to do is think about this in comparison to what about if all the symbols were, in fact, numbers? What about if A was, say, 4, and then minus B, that's just minus 3, and then that's equal to 2? So these symbols just represent numbers. So what about if we just view them as numbers? How does that really change things? And so if it were numbers, the first thing we would do over here is add 3 on both sides. So naturally, over here we would add B on both sides. B is just, you know, a number like 3 or whatever else you could think of. I'm just going to leave it as 2 plus 3, just to match the C plus B thing. We can combine that and make it 5, but I'll keep it consistent. And then what would we finally do to solve for X in that rightmost case? You would divide by 4. We would divide by 4 to get X by itself. And the point is that over here, 4 is now A. So we would divide A. And that would be your answer. So hopefully that's okay so far. It looks intimidating because of all the letters, but sometimes relegating them to numbers gives you a good insight on what the symbolism represents. So with problem 2 over here, I immediately see a fraction. So I immediately think least common denominator. Now, if all of those letters were in fact numbers, then we would have to figure out, well, what's the smallest number that all of these would go into? But they're not numbers. What's that?
It's QRB.
Yeah, it's QRB. Yeah, it's QRB. So we don't have numbers, we have variables. So remember how we treated, or symbols. So remember how we treated those before. For each denominator, we need to reserve a spot in the LCD for it. So I see a Q, so I'm going to put Q here, times, I see an R, and I see a B. So QRB, or Q times R times B, because I need each letter for each denominator. And now we can multiply everything by QRB. 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 And naturally, there's going to be a nice bit of cancellation. Q's cancel over here. Just give us RB. The R's cancel. And then the B's cancel. We can fill in those corresponding blanks. QB is equal to QR. So again, it looks messy because of the symbols, but this is pretty much the best we can deal with for now. And the problem, since there's not an X, naturally the question is, well, what are we even doing? We want us to solve for B. So somehow we need to get B by itself here. There's only one initial problem with that, yeah, you'd probably like to see, huh? Okay. So, yeah, so naturally we want to solve for b, but there's one issue with that. There's two b's in this problem. It's going to be really hard to get b by itself when there's two of them. So if only there was a way to turn two b's into one b. Well, there actually is. There is a way. We can factor out the common b from both terms, as if they both had an x in common, and we factored out the x. So this is when we factor out, this is the same thing as reverse distributing. So if you were to distribute that last step I had, you would go backwards. We're going the other way because now we just turned two b's into one b, which is great, which is pretty good. So we turn two b's into one b by factoring out the common b. Both terms had b in common, so we factored it out. And now we only have one step left. So one step. Since b is multiplying this stuff, to get b by itself, we divide that stuff. So now b would be qr, so that is a q. Just write it out again. Would be qr divided by r plus q, which is what we divided to get b by itself. And that would be your answer. It may not be the most fun process, but this is how you would work this problem with symbols. There's not many like this in the homework. In fact, outside of these two, there's only two other ones. So hopefully you can follow along given the instructions I provided. Does anyone have any questions before we move on to applications? Because if not, then let's do exactly that. And I'll try to leave problem 2 on the board here a second while I talk about example 3. So yeah, there's some applications that involve linear equations. Start off with example 3, which talks about a college bookstore that marks up a price, that it pays the publisher by 25%, blah, blah, blah. So let's just kind of visualize. What would be more practical is to visualize the situation and maybe rationalize it a little bit. Publisher, of course, publishes a book. They sell it to a bookstore because the bookstore, I mean, that's where we buy our books from. So the bookstore buys it from the publisher for some amount. But of course, the bookstore wants to make a profit off that book. They want to make a profit off of it. They don't want to buy the book and then sell it at that same value and break even. That's not cool. They want to make some profit. So the amount they bought for the book, they're going to spike that up by 25%. And then that 25%, that's going to be their profit. So what this problem is saying is, so there's two prices here. There's the original price of the book, and then there's the price after the 25% markup. So the selling price, what they're saying the selling price was, selling price is $63. That's what you would see in the bookstore. So that means this is post markup. So the final value, $63. The original value is what we're looking for. So it's unknown, but in this class, unknown simply means X. So that was the original value that the publisher charged the bookstore. So naturally, we can set up an algebra problem. X is the original price. We're going to leave a space for the 25% markup. We'll leave some space for the 25% markup. We'll fill that out in a second. And then after all of that, then we get $63. So I guess the question is, what does it mean to mark something up by 25%? Well, 25%, if anything, we don't really treat percentages quantitatively. We normally move the decimal place over. But you don't just have 25% in thin air. You gotta have 25% of something, or else it doesn't make any sense. Plus 25%, normally your intuition should say 25% of what? Exactly, 25% of the original price. So you take the original price, you add on 25% of the original price, that is the markup. And after you do all of that, then you get $63. So this is how retail stores do it. If they add, or, if there's a discount on shoes or something of 15%, they'll take the original amount and subtract 15% of the value of the shoes. But now we have set up an algebra problem. And x plus 0.25x are like terms. So this is going to be 1.25x. That's 1 plus 0.25. That's like terms here, because there's an understood 1 out here. So it's 1 plus 0.25, which is 1.25. And you should get $50.40. Check the measure. 63 divided by 1.25. So that would be the original price before the markup. So it looks like the bookstore got a profit of about $13 for this book. Roughly $50 originally, $63. The difference is $13. But in any case, the answer would be $50.40. Anyone have any questions for this word problem? All right, let's look at example 4 as well. A perimeter of a rectangular window. Well, naturally, I think apply some geometry here. So there's some rectangular window. The perimeter is 40 feet. Does anyone in here remember what a perimeter means?
What?
A perimeter?
The area is like two sides multiplied by each other, and then the perimeter is like all four sides.
Yeah, the perimeter is adding all 4 of the sides together. So the perimeter in general is equal to 2L plus, yes, plus 2W. Because there's 2 widths, because it's a rectangle, the width is going to be the same. So there's 2 widths, 2 lengths, you add all those together, and this is the formula for the perimeter. So we know that that is 40. We also know, make some more room here for this rectangle. We also know that the width is 6 more than the length. And the length is, well, just the length. So it says that the width is just 6 feet more than the length. So It's the length plus 6. So if we take that perimeter formula that we had, well, we know that the perimeter in total is 40. And we know that the width, well, we can get rid of one variable by exchanging the W with 6 plus L. Because we know that the width is 6 plus the length. So we just went from 2 variables to 1 variable, which means this is something we can do. And we can solve for L as if it were X. So we can distribute here. 2L plus 12 plus 2L. For L is equal to 28. And I get that L is 7. So the length would be 7 feet. It wants to know the dimensions, so we're going to go ahead and find the width as well. Yep. So the width is 6 plus the length, which is now 7, which is 13. So the width is 13 feet, the length is 7 feet. So that's 2 of, I think, 4 or 5 application problems from the homework. Does anyone have any questions before we move on to the final stuff? All right, well, so we were talking about, in the previous chapter, we talked about converting from inequalities to interval notation. And we're going to do that a little bit more here. So primarily, they're both used, so inequalities and interval notation are both used to represent intervals. They both have their own versatility. Inequalities could be used to algebraically manipulate and move stuff around because there's variables, as you can see in the setup for 1 and 2. We can move the x variables around and treat it as if that inequality symbol was an equal to sign. We cannot do that with interval notation. However, interval notation is a lot more compact of an answer. It's a good conclusion, and inequalities are good at applying algebraic steps. As we'll see here, for problem 1, I see a fraction, I instantly think LCD. There's only one denominator, which is 5. So the LCD has to be 5. Really nothing to compare. So we're going to multiply everything by 5. And yes, that whole expression on the far left is one term. There's terms within it, but it's one term entirely. So I only have to multiply 5 one time. But here, the 5's cancel, and we're left with just x minus 8. It's less than 5 times x plus 16 times 5. Is that 80? Should be. And from here, like I said, we can treat this as if the inequality symbol was an equal to sign, and we combine like terms. So subtract x on both sides. Eight is less than 4x plus 80. We subtract 80 on both sides. And so we get that negative 88 is less than 4x, or negative 22 is less than x. Now it says, express your answer using set notation and interval notation. What we have is set notation. So we found set notation. It's not interval notation. Interval notation is just one step further, but set notation is a solved inequality. That's it. Just whenever you get x by itself. That is set notation. We talked about how to convert inequalities to interval notation. So if x is greater than negative 22, then that means it's going to be approaching positive infinity. Negative 22 with a parenthesis, and then infinity. And this would be the interval notation. So if it asks you for either or, then these would be the two answers. Anyone have any questions about this so far? If not, let's move on to problem 2, which is a compound inequality. Compound because there's two inequality symbols, ultimately. So that means if you're trying to get x by itself by, say, adding 6 to get rid of the 6, then you have to do that to all three sides. So 0 plus 6 would be 6 over here, and then 2x by itself in the middle, and then 4 plus 6 is 10. Finally, by dividing by 2, you'd have to do that to all sides. 6 divided by 2 is 3, and 5. So this would be the set notation, because now x is solved for. And in interval notation, this would be 3 with a bracket, because there's an equal to, and 5 with a bracket, because there's an equal to.
So it would be the other set of brackets if it was closed, like you didn't have it would just be it wouldn't be the inequality sign in the little line.
Yeah, so if you didn't have the equal to part, you would use parentheses for that corresponding number. So if you had instead something like this, and that would equate to bracket on the 3, but parenthesis on the 5.
Okay.
It's how the number equates to the equal to part that's adjacent to the number, right next to the number. So if there's no other questions, there's only 2 quick problems I need to conclude with, and then we will be done with this section. So we start talking about this idea of reciprocal properties, which is a very concentrated thing. In fact, it simplifies very nicely in 3 or 4 cases. And I wrote out all the cases. In the first 3 cases, what they all resort to is if you are given an inequality, if you're given an inequality with one of these weird looking negative exponents, in 3 of these 4 cases, you just toss the negative exponent. Anytime you have a greater than sign, you toss it always. you have a less than sign, it depends on what the number is. Toss negative exponent for those. And then there's this one final case here, which means you just say the answer is no solutions and you move on. Has to do with the even exponent, which makes things positive, but being less than 0 is negative. So there's kind of a contradiction there. So for a problem such as, say, example 6, this seems to follow the negative first power less than 0. And you could just simply get rid of it. So I'm going to rewrite the problem, and it's gone. I just got rid of the negative exponent. That's it. And I'll work out the problem as if just this problem. And negative 5 over 20 simplifies to negative 1 over 4. So I went ahead and just did that. They want the final answer in interval notation. So the interval notation here would be, well, x is less than this number. So it's going towards negative infinity, all the way up to negative 1 over 4. And we use a parenthesis because there's no equal to component here. So this would be the final answer. We have one more problem we need to knock out right fast, and it's the domain of a square root. And it says if you're looking for the domain of a square root problem, it says if you have a square root problem that you're trying to find the domain of, you can get rid of the square roots, provided you set all of that greater than or equal to 0, no matter what. We've done problems like this before, but this is another way of looking at it. And then we solve it. You get 2 to infinity, because we're going to put the answer in interval notation. That is great timing because I am out of time. So like I said, I pushed this homework back a few days. I'm going to send out an email, maybe maybe a little bit after noon, and just remind everybody what's going on with the class, with all the due dates and everything.
What pages on the workbook are we supposed to do, like 9 and 10?
I can't remember offhand. I believe I sent out an email about all of it. If not, I'm gonna just reiterate the workbook pages again. Friday, yeah. Other than that, if you have any questions, I'll stick around, or you're welcome to go. Have a good day.